Hello everyone, I would like to present to you our work, Multi-Floor Danger and Responsiveness Assessment with Autonomous Legged Robots in Catastrophic Scenarios. Our work is based on the DRABC protocol adopted by first responders. The acronym stands for Danger of the Scene, assess the response level of the person, check if the airways are obstructed, if the person is breathing, and if there is any circulation. We want to develop an autonomous robot that completes the first two steps of this protocol autonomously. It should explore as much of the building as possible and, if people are detected, collect information about their health state and their response level, all before rescuers arrive. To do so, we implemented an exploration strategy. The robot should start exploring the environment that in general will be on multiple floors. The exploration algorithm is based on the work described in the paper Autonomous Robotic Exploration based on multiple rapidly exploring randomized trees. The exploration algorithm is frontier-based. Frontiers are areas of space between known and unknown space. The robot should move towards those areas to gather as much information as possible. We propose an innovative metric to evaluate frontiers based on different parameters. For the evaluation of each frontier, we propose a sum of gains and costs with a negative sign. Each factor multiplied by a weight to be able to control the behavior of the exploration. Highlighted are the parameters that were present in the article by Umari. The first term is the information gain that represents the square meters of unknown space in a circular area around the frontier point. The second term is a cost and it is calculated as the Euclidean distance to the frontier. The third term takes into account the value of continuing exploring this floor versus changing floor. When reaching a new floor, the number of square meters explored will increase very quickly. It will then slow down if the robot keeps moving in the same floor, since it discovers only small frontiers, like corners. Our goal is to avoid this slowing down. This gain measures the square meters of unexplored space in the floor, either the one the robot is exploring or the one the stairs take to, based on the assumption that in general building will have a maximum area that is the same for each floor of said building. This gain it measures how much space can be at maximum explored on the floor of the frontier. The fourth and fifth term are optimization terms. They don't weight as much as the others and they regulate how the robot will move. They will give a preference to frontiers in front of the robot. We will assume that this system will be used in public buildings that usually have long corridors, and the rooms open up around the corridor. In order to explore as fast as possible, we think that the robot will first have to explore the hallways, moving straight, and only after that it should enter the rooms. The orientation gain will give a positive gain if the robot is already moving in the direction of the frontier. It depends on the angle between the line connecting the robot to the frontier and the current orientation of the robot. The fifth and last term is a cost and it depends on the path the robot has to take. It measures the ratio between the Euclidean distance and the length of the path the robot has to follow. The path is calculated using the move-based algorithm and its length is evaluated. If the path cannot be found, then the cost is saturated to a large number to avoid for the robot to move towards an unreachable frontier. Notice that if the Euclidean distance and the length of the path are the same, then the cost will be 1, that is the minimum value. In order to evaluate our algorithm, we use the Spot robot from Boston Dynamics, a robot able to climb stairs and obstacles with great mobility. Each exploration experiment lasted 10 minutes. We hypothesized that rescuers will take about 10 minutes to reach the building. In each exploration, we recorded the number of explored square meters at every minute. We ran 9 different explorations, changing between different values of the newly introduced parameters and keeping the weights for the information gain and the distance cost the same. Our baseline trial had the weights for the 3 new parameters set to 0. Then we tested the system with the floor gain set to 4 different values, and for each value we repeated the exploration with and without the optimization parameters. In the graph on the left, we can see the results for all of the experiments. It is important to notice that depending on the time we look at the graph, we have a different best performing set of parameters. In the beginning, exploration that prioritized the full exploration of one floor performed better. The robot is able to explore a lot without wasting time climbing the stairs. After a while, instead, better performances are obtained if the robot explores a portion of each floor and then climbs stairs. From this, we can conclude that, depending on the time frame we suppose the robot should operate autonomously, we should decide a different set of parameters. On the graph on the right, instead, we have the areas explored after 10 minutes. We have in blue the experiments without the optimization parameters, and in red the optimized trial. It is possible to notice that all trials perform better than the baseline, and that for each value of the floor gain, we obtain better results if the optimization is active. We can see a general increase in performance while increasing the value of the floor weight, apart from the last one, where the performance drastically decreases, due to the fact that the robot loses a lot of time climbing the stairs, and in that set of parameters, it explores really small areas of each floor before changing floor. For the second step of the DRABC, assess the responsiveness of the person, we employed camera-based techniques and audio-based ones. For the camera, we mounted on top of the robot a Kinect camera, and we used the media pipe framework to extract key points. From the elaboration of said key points, we were able to classify the position of the person as sitting, laying down, or standing. We are able to detect if the person is blinking and also if the person is moving. For the audio-based evaluation, we asked the person 3 questions and we recorded their answers. To obtain the transcript, we used the Google Web Speech API that works connecting to the internet. This is a major drawback since the infrastructure to provide internet might not be available after a disaster. For this reason, we are currently working on implementing an offline algorithm. In conclusion, we implemented a new policy to explore buildings that have multiple floors and a strategy to assess the responsiveness of people after a disastrous event. We were not able to integrate the 2 tasks due to hardware limitations of the Kinect camera that has to be connected to a power supply. To solve this, we are currently working on using the Intel RealSense camera instead, and we are trying to implement offline speech recognition algorithms and test everything in more challenging environments. Thank you very much for your attention.